presentation of this session. As some people may notice that the three speakers, the title share one topic like poll skipping. So different from the other days, today we will first, every three speaker will give a talk first, and then we will have common discussion after all three talks finished. Of course, each end of each talks, we will have one or two short questions. And the first speaker is Keun-Young from GIST. He will talk about quantum matter and quantum information with holography. Please start.
Thank you. Yeah, but my specific topic is chaos diffusion and poll skipping. Okay, good. Thank you for introduction. As Yoon-Suk said, the three speakers are talking about just one paper. That's this paper. My plan is we just wanted to make a very short talk, not to bore people. So I'm going to just introduce the just the background materials. So my talk is not really related to this research. And after my talk, Victor and Mitsuhiro will talk about really about this paper. So my talk is just a general setup. And actually, this morning, Jan already talked about many things in my slides. He spoiled my slide. So that means I can be more quick. So I would like to thank Jan about that. Okay, so my name is Keun-Young and I'm here in Gwangju. And some organizers are here, APCTP, which is located at the Pohang, and Seoul is here. So now I'm sitting here. Okay. Okay, it was not just a minute. It was not enter full screen. Okay, this is better. Good. First, let me start with poll skipping. This word, if you know, it's very simple word, but if you didn't heard about this before, this is very mysterious. So let me explain about that. So it's about the property of the retarded Green's function. So in general, in momentum space, the Green's function look like this, B over A. And the Green's function itself is a very important physical object in applications. For example, it can give us a conductivity or shear viscosity. So very useful object. And here, the poll skipping means poll is skipped. That means here the denominator A, if denominator A is 0, then we call poll. And if B is also 0, then it's not really poll, it's something else. So then in that sense, it's a poll is now skipped. And that can happen at some specific omega and k. So that I will call omega star and k star. And as you very well know, this 0 over 0 means it's not well defined. Of course, sometimes it can be defined, but usually in general, it's not well defined. It can be understood also in the sense of this expansion. So this Green's function can be linearly expanded around omega star and k star. And if you do the tail expand, denominator and numerator, and the first term, leading term, by definition, both are 0, then we have this expansion. So then, as you know, as you can see here, the value of this Green's function is well defined at finite delta omega and delta k, but it's not well defined when delta omega and delta k goes to 0. That means it depends on this slope. So the meaning of poll skipping, okay, let me summarize. The meaning of poll skipping is at some specific point at the momentum space, which gives a 0 over 0. That means the Green's function is not well defined at that point. Okay, this kind of a concept first introduced in this paper, 17. Actually, Konrad talked about this pole skipping in this workshop. And there were many developments after that. And you can see graphically what pole skipping means in this plot. This is omega, and this is k. Now this is imaginary k. And this blue, you can say this is a zero line, and the red is the pole line. So in this space, now this star and white circles are basically pole skipping points. Okay. So, but I would like to make this clear. Even though we can define pole skipping by identifying pole line and zero line, but you can also identify this by saying, for example, you can think about A equals 1 and B equals 2. That will give us a line. So let me draw here. So you can think about, this is the blue line is zero line. So you can think about, for example, this is a line which gives, for example, B equals 1. And you may say, this is, for example, A equals 5. At these points, the Green's function is not well defined, but it's defined along this path, right? It can be 1 or 2 or 5 or 0 or infinite. So the pole skipping really does not mean some specific things for poles. You can identify pole skipping point by identifying any two lines. So that I want to make it clear. Okay. Good. So then, so now the question is why we care about the pole skipping points. The original motivation was the relation between pole skipping points of the Green's function of this energy density. Okay, this energy density Green's function. So there may be other operators in general, but let's focus on the energy density operator. Then this Green's function may have a pole skipping points, and actually it can have infinitely many pole skipping points, but some specific one, omega star is I lambda L, and k star is I lambda L over VB. Now I have to what lambda L and VB. But so the point is this. So by computing this pole skipping, you can compute this omega star and k star. And by computing some other, okay, let me do it again. So this lambda L can be identified by the quantum Lyapunov exponent, and VB can be identified by the butterfly velocity. So these two quantities are related to the quantum chaos and can be computed independently in other methods. So suppose you know what lambda L is, which is 2 pi t, and what VB is by doing some independent computation. So you know the answer. And surprisingly, just by computing this two-point Green's function, you recover these two parameters. So seemingly they are unrelated, but somehow this two-point Green's function knows about the quantum chaos. I think that's the first moment people get interested in the pole skipping point. Now I have to say about what's the meaning of this quantum Lyapunov exponent and butterfly velocity. Okay, it goes back to the Jan's presentation. So let me speed up. So there are three kinds of, there may be more, but there are three representative ways of the studying quantum chaos. The first one is called the spectral chaos. It studies the energy level distribution and see how that distribution is similar to the random matrix theory. And the other way of studying quantum chaos is the eigenstate thermalizing hypothesis. And the third way is which is called the scrambling chaos, which I'm going to discuss in this talk. It starts from this classical chaos analogy. So initially, the displacement is delta Q, and as time goes on, delta Q T is the displacement. And if this increases exponentially, then we call that the classical chaos. So this phenomena can be described by this quantity, and this is expressed by the Poisson bracket. And now this is a classical chaos. Then we may ask, what is the quantum chaos? As I said, there are many versions of quantum chaos, but from this starting point, we can simply quantize this Poisson bracket with a commutator by upgrading this to the operator. And then we can define this commutator squared, and this is called a C. So you can remember that as a commutator. And this minus is introduced to make these all things positive. And now this is the originally just QNP, but we can upgrade that to the just general Hermitian operator. Now we can also upgrade to the local operator. So this is the development of the concept of scrambling chaos. And interestingly, this quantity can show this behavior, exponential behavior, and we call this lambda L is a quantum Lyapunov exponent, similar to the classical Lyapunov exponent. And this vertiply velocity says how much this quantum chaos is spread through space. So then we have these two quantities, and these two quantities can be computed by a different method and also can be computed by this pole skipping method. So let me describe a little bit more about the scrambling chaos. Here, this is just a commutator squared, and as I just explained it. And also, this was also appeared in Jan's presentation, and we can define two states. And then this C object here, commutator squared, just algebraically explained in this way. So now I define the two quantities, F and N is nothing but just the inner product of the same state, and F is just inner product of the different state. And as Jan said, so this N is basically order one number, and so the exponential behavior, information of the exponential behavior also can be recovered by this object, real F. And this F looks like this. And so because of this form, we call it out of time autocorrelator. So shortly OTOC. So people sometimes study just the OTOC and sometimes study this commutator. So anyways, the physical meaning of this scrambling is this. So at some point, this is the operator V and W at t equals 0. And as time goes on, this W operator grows in this space. And at some time t star, it spreads all over the physical or internal space. Then this time is called the scrambling time. Okay, good. So this is I think I have to skip this about the general idea of holography because everybody knows. Okay, good. Okay, good. Now let's look at the simple example of the pole skipping phenomena. But now I'm going to show it in a very a little bit different way. Okay, so let's focus on the scalar field. This action is scalar field action, the standard one. And as a background metric, so we choose Eddington-Finkelstein coordinate, and we consider equations of motion and this Fourier expansion. Then we have a ODE equation along the holographic direction at momentum space. This is very standard story. And if we look at the solution near boundary, then you have this expansion, and the power is related to the mass of the scalar field. And near horizon, you have this expansion. But because we are doing the Eddington-Finkelstein coordinate system, this alpha is 0 or some value. Okay, so normally what happens is this. Normally alpha 1 equals 0 is a regular solution, and alpha 2 is the singular solution. It's not regular solution. So we just drop out this second solution. Okay, so that's the boundary condition near the horizon. And near the boundary, we have two independent solutions, phi A and phi B. But because of the constraint at the near horizon, these phi A and phi B are related. So that's how we have Green's function here. So phi B over phi A, that looks free near boundary, but actually they are related very, very close to the horizon. Okay, that's how we define Green's function uniquely. If not, they can be anything, right? But that can be unique because of the near horizon condition. So in short, regularity condition at the horizon fixes this Green's function. However, there is some special point. For example, this omega is special. So for example, omega n is minus I 2 pi t n. Then this again becomes a positive integer. That means you have two regular solutions in the horizon. That means you don't have any relation between phi A and phi B. It cannot be determined uniquely. That's basically the appearance of the pole skipping points in the viewpoint of the near horizon analysis. Okay. So, okay, I just repeated for your convenience, scalar field equation, near boundary, near horizon expansion, and Green's function. And this is the story I just told you. Now, this omega can be, actually, n can be 1, 2, 3, 4, and infinite. So there are many, many pole skipping points. So if you want to have a more and more, let's call the higher mode pole skipping points, then you need to understand the geometry far from the horizon in this sense. So your equation of motion can be expanded in terms of R minus R0. So then you can solve this equation order by order. For example, you can first solve S0 equal S0 sub 0 is 0. Next, you can solve S1 is 0. Next, you can solve S2 is 0. So when you solve order by order, then you will recover omega 1 and omega 2 and blah, blah, blah. So you can have a higher modes. That's why you can have this one. So this is the first mode, and this is the second mode, and this is the third mode and fourth mode. And also you can notice in the first mode, there are 2 points, and the second mode, you have 4 points. Probably next to you have 6 points, something like that. That can be understood by this general formula. So let's make this more generalized. So this is the summary of these very nice 2 papers. You can, especially for the second one, I'm just using the second one formalism. The bulk scalar field or bulk Maxwell field and gravitational perturbation, except sound modes. So everything can be formally expressed in this way. Now here P and Q is this. So actually this is, now the R equals 1 is a regular singular point. The important point is now P is 1 over R minus 1 and Q is also 1 over R minus 1. Mathematically, Q can be 1 over R minus 1 squared to be a regular singular point. But because of this, comes from the equation from the background matrix. So because of that, this R minus 1 comes from the in-blackening factor and it's almost fixed. So near horizon, everything is determined by these 2 terms. And interestingly, P minus 1 is 1 minus I omega, something like that. So if you make equation order by order, then by expanded solution, by this expanded solution, then you will have a matrix equation. And here, Mij is linear to omega and quadratic to Q squared. Good. So then, in order to have the pole skipping points, we can solve this equation order by order. The first one is 0 equal n1150 and m1251. So in this case, if m110 and if m12 is 0, that means 50 and 51 both are free. And that means at near horizon, you have 2 independent solutions. So Green's function is not uniquely determined. And these two conditions gives us the omega equals 1. Now this omega is the in unit of 2 pi t. So this is the first pole skipping point. And Q has this structure, omega and Q squared. So this is second order equation of the Q squared. So we have 2 points here. And similarly, in order to have a higher order points, you need to have a 0 up to here. So up to here. So n11, phi 1, phi 0, m12, phi 1 equals 0. And at the same time, m21, phi 0, m22, phi 1, m23, phi 2 is 0. Then the condition is actually m23 is 0, and the determinant of this equation is 0. And that gives us another pole skipping point. And in general, you have this formula. So what I want to say is that getting the pole skipping points by analyzing the near horizon geometry is very, very easy. I think that's the key point I want to say. It's just the ODE. However, in general, it's not easy to compute the quasi-normal mode. So this is a little bit technical point, but a very interesting point. Okay, let's go to the energy density case. Now I showed you this example by using Scala because Scala is easy. But however, if I want to do metric, then I have to deal with many, many components. Everything is coupled. It's more complicated. However, if you do correctly, then this energy density Green's function also have these pole skipping points by a similar computation, and we can get some omega star and k star. And this value turns out to be the same as the Lyapunov exponent and the Lyapunov exponent divided by butterfly velocity. And this is computed independently by other methods, which can be explained by Victor later. Okay, now I just talked about the pole skipping points and the chaotic behavior, but as a final remark, I want to show you the diffusion case. So in this case, actually this is a part of a sound mode. So in general, there should be a sound mode. But if you think about the case where momentum relaxation is very, very strong, then propagating mode almost disappear, and then mode becomes diffusive. So here there are two graphs I want to explain. And first of all, okay, so this dot, dot, dot is the exact quasi-normal mode. Okay, and near this omega equals 0 and k equals 0, it gives us a diffusion. Sorry, in this, okay, I have to start with the right-hand side. It is a diffusion case. Now this M is the momentum relaxation. So in this momentum relaxation case, if momentum relaxation is very, very strong, it's a 100 and it's 1 over 100. So if we want to understand diffusion, we have to think about the this case, right-hand side case. And this curvature gives us the diffusion constant, hydrodynamic mode. And then this, the black dot, dot, dot is the exact quasi-normal mode. This should be computed numerically. We don't have any analytic formula. And this point exactly is the first pole skipping point. So this one, this point is this. Okay, now suppose, now imagine you don't want to compute the quasi-normal mode. That's a very, very complicated numerical calculation. But you just want to know the rough idea of the quasi-normal mode in this complex space. Then what you can do is you can simply do near horizon analysis. Then you can find out these points. And then next, you will find out some point somewhere here. It's discrete. But you can have a rough idea where the pole is by just computing pole skipping point instead of poles. And something more here is, in this case, in this very special case, you can even predict the hydrodynamic diffusion by just looking at these points. If this blue line exactly passes through this one, then this is just a diffusion curve. And by just computing near horizon quantity pole skipping points, which has something to do with the chaotic behavior, but you can know about the diffusion constant. Okay, that's the basic idea about the relation between diffusion and chaos. However, unfortunately, this kind of a nice relation only appears in this energy density case. So you may ask if this nice phenomena also appears as scalar or vector or fermion or blah, blah, any observables. So far as I know, there's no no nice relation about this. Okay, but probably that has something to do with only chaotic behavior. I guess Mitsuhiro may talk about that later. Okay, so I have to summarize. So you may think about the many generalization, higher order pole skipping. So you can think about the higher order pole skipping and other geometry like Jan's morning talk and other scalar vector metric fermion and relation to effective hydrodynamics and analysis from field theory, purely field theory without holography, and some generalization to the curved space boundary field theory. This is the main topic of the Victor and Mitsuhiro's talk. So there are many, many works on here. So let me summarize here. There are many comparisons. So here, first of all, the 4-point OTOC function. Somehow it has something to do with the 2-point retarded Green function. This is very interesting. 4-point function is not easy, but 2-point function is relatively much easier. But if we know the information of some of this by computing this, then that will be great. Also, this phenomena, pole skipping phenomena happens in field theory and gravity. So we can think about the duality between them. And the pole skipping point, what I described is computed only near horizon analysis, but Green's function is defined near boundary. They can be, of course, they can be related, but their relation sometimes is straightforward, sometimes it's a little bit subtle. And sometimes we can understand everything analytically, and sometimes we can understand only numerically. So there are many interesting connections in this point of view. So there are many supporting evidences from either gravity or field theory. However, it's not easy to compute everything analytically in flat space. So for better understanding in the analytic viewpoint, it will be good to have some analytic formulas. Then it's, advantageous to go to the curved space, so hyperbolic space. And the main idea is the hyperbolic space, the thermal physics in the hyperbolic space can be conformally is equivalent to the physics at the flat space. So by using this conformal transformation, we may understand this thermal physics in the curved space relatively easily. I think that's in a technical point of view, that's the main theme of the Mitsuhiro and Victor. Okay, thank you for your attention.
Any other questions? Because I think that Victor and Mitsuhiro will give more detail. So
okay.
I think it's better to wait until Mitsuhiro and Victor finish the talk, and then after that we will have discussion session.
Okay, good.
Yeah. Next speaker is who is Victor?
Yeah, Victor.
Oh, yes. Sorry, I forgot to turn on my microphone. Okay, so can I share my screen?
Yes.
Okay. Okay.
Okay, good.
So can you guys see my mouse?
Yeah.
Or should I use? Okay. Just in case, I'm gonna use this spotlight. Oh no.
So, are you ready?
Oh yes.
Okay. Next speaker is Victor Jahnke from GIST. He will talk about scrambling and pole skipping in hyperbolic black hole. Please start.
Okay, so thank you very much for the introduction. Let me first thank the organizers for putting together this very nice conference and for the opportunity to give this talk. So I'm going to be talking about scrambling and pole skipping in hyperbolic space. So this talk is based on these two papers, which were done in collaboration with Keun-Young Kim, Mitsuhiro Nishida, Young-Jung An, Hang-Sik Jung, and Kyung-Sam Lee. Okay, so that's an overview of my talk. I'll briefly describe the gravity setup and the corresponding scrambling properties. And for the most of my talk, I will be discussing pole skipping. Okay, so pole skipping is a phenomenon that takes place in planar black holes, and it suggests a highly non-trivial connection between scrambling and hydrodynamics in the boundary theory. So one of the questions that we would like to answer is that whether pole skipping also takes place in non-planar black holes, and whether is it still related to scrambling. So to answer that question, we study pole skipping in hyperbolic black holes in ADS. And in particular, we consider a Ringler ADS geometry, which allows us to obtain some exact results in both sides of the ADS-CFT duality. This is actually our main motivation to consider hyperbolic space. So in this talk, I'll give you the ADS perspective, and for the CFT perspective, I will refer to Mitsuhiro's talk. Okay, so let me first discuss the gravity setup. We are going to be doing calculations in the context of Einstein-Hilbert gravity, and we are going to consider asymptotically ADS hyperbolic black holes. So these black holes are dual to CFTs that live in hyperbolic space. And sometimes it will be useful for us to consider a special limit of this metric in which you recover a Ringler ADS geometry, which simplifies things a lot and allows us to get some exact results. So I'll first describe the scrambling properties of these black holes, and then I'll talk about pole skipping. Okay, so to study scrambling, by scrambling, I mean the late time vanishing of OTOCs. And Schenker and Stanford proposed prescription to compute OTOCs holographically. And in this prescription, you basically write down the OTOC as an overlap amplitude in which you have an in state, which is described in the bulk by two particles heading to collide, and you have an out state in which the two particles are leaving the collision region. So these two particle states are described by a shockwave geometry. And it turns out that the boundary 4-point function can be written in terms of a bulk 4-point function, which in general is very difficult to compute. But under the configuration of the above picture, this bulk 4-point function can be computed using the so-called iconal approximation. So this bulk 4-point function is just given by a phase, and this phase, it's basically the classical action of these bulk particles. So by performing this calculation, one realizes that the OTOC is essentially controlled by this phase shift, which, as mentioned before, it's basically characterized by a Lyapunov exponent and a butterfly speed. B here is just the collision impact parameter. Okay, so by performing this calculation for a Ringler ADS geometry, we get this result. And this result, as you can see, at very large times, the OTOC goes to 0, and there is some intermediate region of times in which the OTOC has this typical exponential behavior. So for a Ringler ADS geometry, the Hawking's inverse temperature equals 2 pi, so the Lyapunov exponent equals 1. And the butterfly speed equals 1 divided by d minus 1. And this matches the CFT result obtained by Permuter some years ago. So in considering more general hyperbolic black holes, we can also perform this calculation. And in this case, the butterfly speed is temperature dependent. So the Lyapunov exponent is given by the typical universal result, and the butterfly speed, when the temperature equals 1/2 pi, we get the Ringler result. And for very large temperatures, the black hole is very large, the horizon radius. So we recover the planar black hole result. Okay, so those are the scrambling properties of these hyperbolic black holes. And the question now is whether we can reproduce these results using a pole skipping analysis. Okay. Okay, so I have some. Okay, so pole skipping, as Keun-Young already explained, the pole skipping points can be computed by just looking at points at which a retarder Green function is not well defined. So for the energy density correlation functions, the pole skipping points are related to the Lyapunov exponent and butterfly speed. And as I told you before, this suggests a non-trivial connection between hydro and chaos. So now the question that we would like to answer is whether there is a form of pole skipping in non-planar black holes. Okay, so a technical point is that, okay, in the case of planar black holes, the equations of motion involve the Laplacian in flat space. So we can perform a planar wave decomposition of our fluctuations, in this case, the metric field. So that means that our Green's function depends on omega and k. In the case of hyperbolic black holes, the equations of motion involve the Laplacian in hyperbolic space. So we can no longer expand the solutions in terms of planar waves, but we can actually do a decomposition in terms of eigenfunctions of this hyperbolic, this Laplacian in hyperbolic space. In that case, it turned out to be convenient to use hyperspherical harmonics with some complex angle. And in that case, our eigenfunctions are no longer parameterized by k, but actually by an angular momentum quantum number, L. And the pole skipping points will be given by special values of frequency and L. Okay, so we consider 3 types of fields: gravitational perturbations, vector field perturbations, and scalar field perturbations. And as for the gravitational perturbations, by performing a near horizon analysis for the sound channel, we actually checked that the pole skipping points are still related to the chaotic properties that we can get from the OTOC calculation. So that basically establishes that scrambling and pole skipping, the relation between scrambling and pole skipping still holds in hyperbolic space. After doing that, we consider vector and scalar field perturbations. And in this case, we realized that in Ringler ADS, we can actually obtain exact results for the corresponding Green's functions. So for Ringler ADS. For more general black holes, we only performed a near horizon analysis. So let me show you a little bit of this calculation, showing the case of the scalar field. So we consider this action for the scalar field in Ringler ADS, and by this choice of ansatz in terms of hyperspherical harmonics, we can get a relatively simple equation of motion, which can be solved in terms of hypergeometric functions. So by using the holographic dictionary and the usual prescriptions, we can actually compute exactly the corresponding Green's function. And that's the result. The results, it's relatively simple. It's just given by a ratio of gamma functions. So let me just repeat the result here. for your convenience. And the pole skipping points occur at some special values of omega and L, such that the poles of the gamma functions in the denominator and numerator coincide. So we, by finding this exact result, we can actually compute the full set of pole skipping points, which are written here. So here I should remind you that 2 pi t equals 1. And we are, okay, so we are going to be interested in the leading pole skipping points, which are the ones with the biggest value of imaginary frequency. So for the scalar field, we got this result. And as you know, as you might notice, we got two solutions for L. So here it's a summary of our results for scalar, vector, and spin 2 field. And this result can be summarized below. So if you consider a field of spin j and conformal dimension delta, the above result can be summarized by this formula. So you can see that the two solutions for L are always the same, but the special frequency actually depends on the spin. And the above result has a can be derived and explained by a CFT analysis. So I'm gonna let Mitsuhiro explain this point so I don't spoil his talk. And
ask a question.
Yes.
So here, L is a real number. Is it due to that you choose an imaginary chi?
Sorry, can you repeat the question, please?
So here, L star is a real number. I mean, it's different from the planar case. I mean, the K star is a pure imaginary, right?
That's right. That's right.
You choose an imaginary chi in the spherical function.
So
For
yes, usually when you have the pole skipping points, if you consider a planar wave with that pole skipping points, you recover the shock wave profile if you're talking about the energy density perturbations, right? So in this case, also if we consider this spherical harmonics at very large chi, and we plug the pole skipping points here, we recover the usual shockwave profile that we get from the
But the planar case is a pure imaginary number. How can a real number?
In this case is real, but you can also define some sort of K, which is related to L by some imaginary number. But this K only makes sense in the large chi limit, and L here makes sense always. But I think in Mitsuhiro's talk, he uses K instead of L, or he uses both. But yeah, it's possible, but it's not, I think this K, there are several Ks, which depends essentially on which type of eigenfunction you chose here. So for example, here the boundary CFT lives on the line times hyperbolic space. In Mitsuhiro's talk, he lives on a circle times hyperbolic space. So other eigenfunctions are more convenient in that case. But there are some relations between L and K, and indeed L is real and K is purely imaginary, depending on the K you define.
Okay, thanks.
Yes, so one comment that I would like to make here is that we get two L's, and I think only one of these two L's are more physical, because L plus leads to a shock wave. If I consider energy density perturbation, L plus leads to a shock wave profile whose spatial part decreases exponentially as you move away from the source. And L minus leads to the opposite. It leads to a spatial profile that increases exponentially as you move away from the source. So by this physical consideration, L plus seems to be the physical one, let's say. But Mitsuhiro have a nice interpretation for this L minus. Okay, so my final remarks is that regular ADS-CFT, it's a useful framework for studying pole skipping, since it allows us to obtain analytical results in both sides of ADS-CFT duality. And the relation between scrambling and pole skipping still holds in hyperbolic space. And finally, pole skipping suggests this non-trivial connection between chaos and hydrodynamics. However, in pole skipping also takes place in hyperbolic space, where, as far as I know, there is no obvious definition of hydrodynamics. So I think this indicates that pole skipping is maybe more general, and it doesn't rely on the existence of hydro modes. So some open questions is that I would like to answer is whether it's possible to define some form of hydrodynamics in hyperbolic space. So maybe there is some relation between butterfly speed and some thermal diffusion. And other question that I would like to answer is whether pole skipping also happens in black holes with spherical horizon. If yes, that would imply that pole skipping happens even in the absence of hydro modes. So it really doesn't rely on the existence of hydrodynamics, as I guess people thought initially. So that's all I have to say. So thank you.
Any short questions or comments?
Hi, Victor. Can you comment on high spin case? You mentioned some form for generic spin J.
Oh yeah, sure. Yeah, so that formula that I showed you, I was just like empirical based on these holographic results. But in Mitsuhiro's talk, he can actually derive this. So that would imply that a higher spin field would have more than maximal Lyapunov exponent. So of course, like, so here, as you can see, basically, if you think about the OTOC calculation, this is the spin of the exchange operator. So if you write down a diagram for this, let me see if I can do this. Draw. Okay, so if you write down a diagram like this, so let's say this is, oh, this is V. And let's say this is W. So here, this is the spin of the exchange operator. So if the exchange operator has spin greater than 2, you would violate the chaos bound. But you cannot have a theory which has like only a finite numbers of higher spin fields. You need to have a full tower of an infinite tower of higher spin fields. And for example, in string theory, you know that if you sum a infinite tower of higher spin fields, you actually end up reducing the Lyapunov exponent. It's less than maximal. So I think these higher spin cases are pathological. So anyhow, like that there's this connection. I think they break unitarity, and from the point of view of and that break of unitarity reflects in the violation of the chaos bound.
So on the other hand, for vector field, so there's a pole skipping at omega equal to 0.
Yes.
Does it mean there is any kind of spatial instability?
So sorry, can you repeat the question, please? Is there any kind of?
So it looks like at some finite k, I'm not sure, the system is unstable, or there's some normalizable mode of the system. I mean,
not that I know of. You mean because the frequency is 0 for the vector field?
Yeah, true. I mean, some normalizable mode at non-zero k. It looks strange.
Oh, okay.
But in the vector case, omega equals 0, that means Q equals 0 is the pole skipping point.
Yeah.
Oh, so I'm talking about the flat space case. For example, Jan. So in the flat space, if omega, in the vector case, if omega equals 0, then k equals 0. The 0 point is the pole skipping point, not the.
Yeah, that's fine. But right now is for omega equals 0, but non-zero k. It seems that there are some modes. I don't know.
But we don't know if k equals 0 or non-zero at this moment.
Yeah. So this, in terms of L,
yeah, this variable L is a little bit different from K. So I think that's a very interesting question. We have to track the relation between L and K later. But so for now, I'm not so sure.
Yeah, I'm sorry. I am also not so sure. Sorry for.
Okay.
Okay, we will talk it later.
Okay, can I make a short question?
Yeah, sure.
Scala and the vector, and for scala and the vector field,
okay,
omega star is as imaginary part is not positive, right?
Right.
So in that case, do you expect any similarity with the chaos?
Yeah. So as you, that's a very interesting point. So for the spin-2 field, that positive imaginary frequency leads to an exponential, a mode that increases exponentially with time. And for the scalar field, for example, it's negative. So it leads to a mode that exponentially decreases with time. So as Mitsuhiro will explain, this contribution to the 4-point function is there, but it is just exponentially suppressed as compared to the one from the spin-2 field. But it's there, like it has like the same form of OTOC, like it has e to the lambda time minus this corresponding space and butterfly velocity. But this, in this case, it's like a negative Lyapunov exponent, let's say. So
I think that will be more clear later when Mitsuhiro will talk about the 4-point function.
I will wait.
Okay, so sorry for my explanation that it's not very clear. But yeah, hopefully Mitsuhiro will correct my mistakes.
Okay, let's thank to speaker again.
Thank you.
The speaker is Mitsuhiro Nishida. Mitsuhiro, could you share your screen? Probably Mitsuhiro will explain everything. Who already raised question.
Now, can you see my screen?
Okay. The last speaker of this session is Mitsuhiro Nishida. He will talk about pole skipping phenomena in CFTs. Please start.
Okay, thank you for giving me the opportunity to talk at this workshop. Okay, for now, I'd like to talk about our study about our pole skipping point in conformal field theory side. This work is collaboration with Keun-Young, Victor Jahnke, Mitsuhiro, Keun-Young, and Gyun-san. Okay, first, I remind you about pole skipping points again. So pole skipping points are intersections between lines of poles and lines of zeros in momentum space of green function. As a toy example, consider green function as omega plus k over omega minus k. So this green function has a pole skipping point at omega equal k equal 0. And at pole skipping points, this green function is not well defined in the sense that g is 0 over 0. Then so from now, I will talk pole skipping points in conformal field theories. Our work is inspired by this group's pole skipping points study in CFTs. They calculated the pole skipping points in two-point function of energy density on S1 times hyperbolic space. And they showed that a pole skipping point is related to Lyapunov exponent and butterfly velocity in holographic CFTs on hyperbolic space. More precisely, they showed that a pole skipping point of energy momentum density is related to the rate time behavior of conformal block with energy momentum tensor exchange in OTOC. So this relation between pole skipping point and rate time behavior of conformal block is universal in any CFTs. And in holographic CFT, this sub-leading term in 4-point OTOC can be approximated by the conformal block with energy momentum tensor exchange, as explained in these papers. And in the bulk picture, this energy momentum tensor dominance is related to the fact that Lyapunov exponent and butterfly velocity can be computed from shock wave geometry, namely gravitonic exchange, as explained in Victor's talk. And this energy momentum tensor dominance is related to hydrodynamics as an effective theory of conserved current in Matteo's talk. Then in holographic CFTs, Lyapunov exponent and butterfly velocity are related to the pole skipping point of energy momentum tensor. And based on this research, we expect that the rate time behavior of conformal block are related to pole skipping points, even in fields other than energy momentum tensor. Originally, pole skipping points were studied in spin 2 case. It is interesting to study effect of spin by comparing pole skipping points in other fields such as spin 0 scalar, spin 1 vector. To see the difference, one merit of CFTs on hyperbolic space is that we can analytically compute a thermal 2-point function. In our work, we check our expectation in scalar and vector case by computing pole skipping points on hyperbolic space. So this is the outline of my talk. First, I explain the rate time behavior of conformal block in OTOC. This behavior can be obtained by an analytic continuation of Euclidean conformal block. Okay, I explain why we consider hyperbolic space. It is known that there is a conformal map between S1 times hyperbolic space and Euclidean space, like this. Now, this tau is Euclidean time with period 2 pi. By this transformation, thermal CFT's correlation function in the hyperbolic space, CFT correlation function on S1 times hyperbolic space can be computed by CFT's correlation function in Euclidean space. So this is a merit of hyperbolic space. And our purpose is to consider OTOC on hyperbolic space. So it can be computed by an analytic continuation from Euclidean correlation function. Then we consider the analytic continuation as follows. First, we introduce this real time t as tau a equal ita plus delta a. And in our setup, real time of scalar operator v is t, and real time of w operator is 0. And spatial distance on hyperbolic space between v and w is order d. And the spatial distance between the same operator is 0. And for OTOC, we need to impose the order of Euclidean time delta like this. So this order is very important for analytic continuation of OTOC. And it is well known that so correlation function in Euclidean CFTs can be expanded by conformal block G. For example, this Euclidean 4-point function can be expanded by conformal block G. Now, this L is the spin of exchange operator O, and delta is conformal dimension of O. So these conformal blocks can be determined by conformal symmetry. So this conformal block doesn't depend on the detail of theory. And they are function of conformal invariant cross ratio, U and V. And to compute OTOC, so we need analytic continuation of U and V. Note that under the time evolution of real time T, this cross ratio V rotates around V equals 0 clockwisely, clockwise like this figure. So this rotation around V equals 0 is important for the analytic continuation of conformal block. Okay. And since this Euclidean conformal block G is singular at V equals 0, so we should consider analytic continuation of G as V goes to exponential minus 2 pi I V. And at the later time, so U and V can be expressed by T and D like this. And by using them, so we obtain the later time behavior of conformal block G like this. For example, let's consider energy momentum tensor as delta equal D and L equal T. So if we consider energy momentum tensor, we can obtain the later time behavior of conformal block like this. So this behavior is consistent with holographic computation of Lyapunov exponent and butterfly velocity in Lindora ADS geometry, as I explained in Victor's talk. Okay. Next, I explain pole skipping analysis in CFT's 2-point function and show that the pole skipping points are related to conformal blocks behavior. Okay, so then by using the conformal map between Euclidean space and S1 times hyperbolic space, so we can obtain CFT scalar 2-point function like this. So this is a scalar 2-point function on S1 times hyperbolic space. Then so we want to compute momentum 2-point function of this position space 2-point function. Now we consider eigenfunction f of Laplacian on S1 times hyperbolic space. So this Fourier transformation on S1 times hyperbolic space was developed by these two papers. Then so after some computations and regularizations, so we obtain the momentum 2-point function by these gamma functions. For example, this figure is a plot of log G with D equal 4 and delta equal 4.5. The horizontal axis is imaginary value of K, and the vertical axis is omega E. And the red line represents pole of G. And the blue lines represent zeros of G. And the black dots are intersection of red lines and blue lines. So black dots are pole skipping points. We can see that there are the leading pole skipping points at omega equal -1. And now K star equal K equal plus minus I times delta minus D over 2. So this is. Now this leading means the largest omega E. Similarly, we can also compute pole skipping points for vector. And in vector case, so leading pole skipping points at omega e equals 0. Then by using this method, so we yes.
Could you remind me what was this conformal field theory?
What was?
Conformal field theory or?
So in this case, so conformal 2-point function, the structure can be determined uniquely. So then in any CFT, this 2-point function is
the theory. I'm sorry.
Sorry.
What was your conformal field theory?
In any CFT.
Any
so
CFT.
Yeah, this 2-point function can be determined uniquely. Universally. So then, so in any CFT, this 2-point function formula is valid. Or this 2-point function can be determined by conformal symmetry only.
In any dimension?
Any dimension. Yes, yes. So any
dimension.
Any D. Yes.
Right. Okay. And you say that the pole skipping point are only at negative imaginary.
Yes, for in scalar case. Yes, like this.
Oh, that's for scalar case.
Yeah, so this is a scalar case. Yes.
So when did you say it is a scalar?
Because this is a scalar 2-point function.
Oh,
so, for example, in vector case, we should consider vector 2-point function.
Okay, that was what I was looking for.
Okay.
A question: how about 4-point function? In the case of
4-point function.
Yeah.
Of course, 4-point function depends on the detail of theory. For example, free CFT and holographic CFT's 4-point function different.
Yeah. Yes, but then how can you obtain the asymptotic behavior? I mean, so monodromy structure doesn't matter for, and also the structure constant doesn't matter for the this late time behavior.
To obtain the late time behavior of conformal block, so monodromy of conformal block is very important.
Yes.
And but to obtain the late time behavior of 4-point function, so we should consider this summation. And generally, this is very difficult. Yes. But in holographic CFT, so we can compute late time behavior by using the dominant contribution by energy momentum tensor exchange.
I'm sorry, what
or in other
holographic CFT?
Okay, holographic CFT means consider CFT with this condition. First, large degrees of freedom and sparse spectrum and no light higher spin single trace operator. So we call CFT with this condition as holographic CFTs. And in this case, if we consider conformal dimension of V and W are large, and we also assume, and if we also assume unity bound, we can explain that. So energy momentum tensor exchange is dominant in OTOC.
I see.
Because of, I think this large degrees of freedom and no light higher spin single trace operator is a very important property for energy momentum tensor dominance.
I see. I see. Thank you.
Okay. Then so we found that leading pole skipping point at omega e star equal L minus 1 and k star equal plus minus delta minus d over 2 for scalar and vector case. And let's consider eigenfunction at these leading pole skipping points. At small rho or large d, we can obtain this exponential behavior. Now, L in Victor's talk corresponds to minus d minus 2 over 2 plus ik. And at the leading pole skipping points, so we obtain these two exponential behavior. So this exponential behavior is consistent with late time behavior of conformal block and its shadow conformal block. Then, so we have shown that the leading pole skipping points of scalar and vector 2-point function in hyperbolic space are related to the late time behavior of conformal block in 4-point ODOC. Okay, so let me summarize my talk. So we study the pole skipping points of scalar and vector thermal 2-point function in CFTs on hyperbolic space. And we show that the leading pole skipping points are related to the late time behavior of conformal block. Note that so this field theory computation is consistent with corollary computation in Victor's talk. Okay, that's all. Thank you.
Okay, now it's open to the discussion session. Maybe you can ask to all the speakers.
May I ask? So, will you explain more about how the monodromy structure, I mean, does not matter in the case of holographic CFTs? Sorry. Yeah.
Sorry. Monodromy structure of conformal block is important. So okay, I'll explain why. So why energy momentum tensor is dominant in holographic CFT. Okay. So first, as I explained, so late time behavior of each conformal block is like this. Okay. So then, so exchange with large L and so large spin and small data is dominant. And if delta V and delta W are large, so exchange of double trace operator is suppressed. Double trace operator means like this type of operator.
I see.
And now we assume this condition. There is no right higher spin. L is larger than 2 single trace operator. So then with this assumption, so dominant operator is spin 2. And if we assume unitarity or unitarity bound, the smallest delta operator with smallest delta is energy momentum tensor. So at late time and large distance, energy momentum tensor exchange is dominant in holographic CFTs.
I see.
This was discussed by these papers.
I see. I see. Yeah. Thank you.
Hi. Do you study for scalar and maybe vector? There is no scrambling?
Yes, because for example, L equal 2 case, so this L minus 1 is positive. But if L equal 1 and L equal 0, this L1 minus is not positive, so this is not related to scrambling.
So that is a little bit surprising news. Because do you have any, I mean, the reasonable intuition why, I mean, whether there is a rapid scrambling or rapid equilibration doesn't happen for scalars or vectors?
I think, sorry, I don't have good explanation, but important thing is if we consider late time behavior of conformal block, so spin is very important for late time behavior.
So just one comment. You say the scalar field has a contribution which is exponentially suppressed, right?
No,
I mean, like my point was just that the contribution is there, but is exponentially suppressed. Just at late times you just don't see it, but there is a contribution.
But the question is, if suppose that maybe some theory contains only, I mean, the spin 0 and the spin
Okay.
1. And do you expect that such a theory, although it is a scale invariant and so on, there is no scrambling?
But now we consider CFT, so we assume that there is energy momentum tensor.
But he's thinking about another theory maybe that doesn't have energy momentum tensor. And then the exchange operator would be, of course, would be outside the context of CFT maps, but the exchange operator would contain a vector and a scalar. Just in such a way that the largest spin case would be a spin 1 or a spin 0. I guess that's the question, right?
Yeah, right. So what you are suggesting is that the if this scrambling has anything to do with the pole skipping, it is suggesting that only when a theory has spins which is higher than or equal to 2, only in that case things are scrambled and early equilibrium is available, which is a little bit surprising.
But more precisely, for general CFT, we should consider this summation. So there is a possibility of cancellation of conformal block. Or more precisely, we should consider resummation of conformal block in general CFT. So then I think there is a possibility that, so even though there is a speed to operator, there is no scrambling because of this infinite sum, or there is because of cancellation between conformal blocks.
Or maybe your sometimes analytic continuation has some blocking or.
Of course, in this discussion, analytic continuation is very important.
Right. So sometimes it could be such that there is some cut, and then
yes.
is not available and so on. So anyway, the result was a little bit surprising to me. Anyway, thank you very much.
Thank you.
Okay, any other questions?
May I ask one more question? So I would like to ask Victor, the second speaker.
Yes.
Yeah, I would like to ask an elementary part. Will you explain again about the graviton scattering part? How
sure.
can you calculate the 4-point OTOC from the graviton scattering? So I didn't know, I don't know, so will you explain again? Sorry.
Oh yeah, sure. So let me share my screen again, just a second. Okay. Just a second. Yes, so you're talking about this slide, right?
I mean, this slide, yes, right. Yeah.
So yeah, so basically, in principle, you can always write down the 4-point function of the boundary in terms of a 4-point function in the bulk, right? So, but this 4-point function in the bulk in general is very complicated because you might have several contributions to this. So the clever trick that Schenker and Stanford did was to consider operators like W operator is a very late operator, and the V operator is very early. So it turns out that when you consider this configuration, well, for example, when you apply the operator V here, you introduce a bulk particle. And if this operator is very early, this bulk particle is traveling very close to the horizon. And the same goes for a very late perturbation that's due to a particle that is traveling very close to the horizon. So when you divide the OTOC in this form, you can see that this actually corresponds to a high energy collision in the bulk, which takes place here close to the bifurcated surface. So under these conditions, you might use this iconal approximation in which you're basically assuming, I have a slide about that actually. It's an extra slide. Yeah, so here. So basically the assumption here is that you have a high energy collision and the impact parameter is fixed. So in the context of linearized gravity, you take this Reggie limit and you can actually sum all the ladder contributions involving graviton exchange. And this is just a phase. This was shown by Luft in the late 80s and by Verlin in the early 90s. So under these assumptions, you can just replace the bulk 4-point function by this phase. And this phase turned out to be just the classical action of these particles. So when you do this calculation, let me go back to that previous slide. When you compute this phase shift, you find out that it scales with the S, which is the energy in the center of mass. And it has some dependence on B, which is the separation between the two operators. So in the end of the day, basically the OTOC is completely fixed by this, the functional form is fixed by this phase shift. And the assumption here is graviton dominance. Like you get this universal result because these scalar fields, these particles are basically exchanging in graviton. And at large energies, this graviton dominates. So you just don't see the contributions, the other contributions, which are subleading. They are there, but they are subleading. So in this approximation, you're just getting the leading contribution. So I'm not sure, was that more or less?
I see. Thank you very much for your kind explanation. Thank you.
Yeah, so if you have more questions, I'll be happy to give you more details.
Okay, any other questions? I have an elementary question to Keun-Young.
So let me stop sharing my screen, sorry.
Okay, I have question to Keun-Young.
Yes.
When you explain this pole skipping procedure from this near horizon analysis,
Yeah.
you are saying that you are request some regulatory condition of this field, and then
just a minute.
okay.
I'm sharing. Yeah, somewhere here, right?
Maybe that one.
Yeah. Yes.
Next slide.
Next. Yes.
So it's very simple question. Okay. Where that is this omega n is like 2 pi Tn.
Yes.
Pole skipping condition at the horizon.
Yes.
So it looks like some Kaluza-Klein tower of time circle, right?
Yeah.
So is it related to some kind of thermalization and pole skipping, or?
Yeah, people say it has something to do with the Matsubara frequency, but to my understanding, there's no deeper understanding about that. But the interesting thing is, if you study a fermion case, then this omega becomes a half integer, like a Matsubara frequency.
Oh,
that's something interesting.
I see. So this Matsubara frequency itself is closely related to the some scrambling or chaos in some sense, right?
Yeah, you may say that.
Okay. Okay, thank you. Is there any questions or comments?
Can I ask a very general question? So, so for these post-gaping points, is it possible that the post-gaping points are not zero? I mean, are not a simple pole, but double pole, like you know, square in the denominator?
Yeah, it's possible. Yeah.
And what happened? You have mentioned you have encountered that kind of example. What's that?
Jan? So actually, we are writing a paper about that. So
Great.
may I tell you about that probably in a week after finishing our paper?
Okay, great. I'm looking forward to it.
Oh, I can tell you in private. Privately.
Okay, okay, okay. Thanks.
Okay, thank you.
Okay, it's time almost finished. Okay, let's thanks to all the speakers in this session.
Jan? Still there, Jan?
Yeah.
Okay, so